Hoover High School AP Chemistry. This is Unit 4 Notes on Thermochemistry. This corresponds with your textbook, Chapter 5. We're doing this differently. We're not having PowerPoint slides for this unit. We're going to go by written notes. And so I'm going to do a reading through of the notes for you. You can read them yourself if you would like. I'll try to clarify any questions you might have, though, in these and help you with pronunciation along the way. So energy is defined as a capacity to do work. Energy can cause an object to move, that is work, abbreviated W, or produce heat, that's abbreviated Q. The change in energy, delta E, is the sum of these two. So change in energy is work plus heat. Q is heat, W is work. Work can never be done with 100% efficiency, which means that some heat will be lost whenever work is done. It is possible, however, to release all of the energy in a chemical reaction in the form of heat. For this reason, chemists study the energy in chemical reactions by measuring the heat released or absorbed without any motion. So if they can eliminate any movement of anything, which constitutes work, then all of the energy will be in the form of heat. And since we have a way to measure heat, and we're going to talk about that in this unit, they can know how much energy is coming out of a chemical reaction. Energy can be divided into potential energy and kinetic energy. Potential energy, PE, is stored energy that can be released. In chemistry, PE is energy stored in chemical bonds that can be released initially in the form of heat, which we'll define later. Kinetic energy, KE, is the release of energy of motion. Motion of a car can also be called mechanical energy. The translation of kinetic energy into a force that causes an object to move some distance is called work. So a good way to keep this concept in mind is think of gasoline that goes into a car is stored potential energy, stored in the form of chemical bonds. When the car moves, this is what you want the car to do. That's what the car is designed to do. That energy is converted into work, which is the movement of the car, and heat. The heat comes off the engine. That's wasted energy. So all of the gasoline that goes into the car is either translated into work or heat. So gasoline represents stored potential energy that a car needs to do work. Take the reaction C8H18 plus O2 gives you CO2 plus H2O. In this reaction, octane, that's what C8H18 is, combusts with oxygen, that is, burns. The rearrangement of the atoms releases thermal heat energy in the engine, which produces mechanical energy, movement of the car, and heat, wasted energy. Temperature. Temperature is the average kinetic energy of atoms and molecules. We talked about that back in the gas laws unit. And again, we're going to call atoms and molecules particles in a solid, liquid, or gas. Although the particles in the solid can't move around, they can have kinetic energy, motion energy by vibrating in place. There's absolutely nothing in the universe that's standing still. Everything has some energy and therefore some motion to it. So look at the rail on the left. This rail, this is a metal rail at 6 a.m. in the morning. It's cold. And then look at the rail over on the right. This is a metal rail at 2 p.m. in the afternoon. On a hot day, it's very hot. So though the rails look the same, the molecules in the one on the right are at a higher temperature, and they're wiggling with much greater kinetic energy. So they have a lot of energy. You just can't visibly see that energy, but they are moving around faster than the same molecules on the metal on the right. So heat. Heat is the transfer of energy between two objects of different temperatures. So the kinetic energy in one object transfers heat energy to increase the kinetic energy in another object. And note that the object can be the air. So when you turn on a stove in your kitchen, you have an object getting hotter, it transfers heat into the atmosphere, which is cooler than the stove. So it goes from higher temperature to lower temperature. So again, give an example of a couple of handrails here. When you touch the cold rail in the morning with your warm hand, This causes heat energy to transfer from your hand to the rail. This causes your hand to freeze. You feel the sensation of cold. When you touch the hot rail in the afternoon, your hand is the same temperature. It's still warm, but this causes heat energy to transfer from the rail to your hand because the rail at that time is much hotter than your hand, and this burns your hand. Temperature is kinetic energy internal to an object. Heat is the outside movement of thermal energy between two objects at different temperatures, from high temperature to low temperature. Another example is this. Let's say you touch that rail. You also brought a cup of water outside in the morning. So it's 6 in the morning, and you put your finger in the cup of water, and it feels cool. It's not cold, but it's cool at 6 in the morning. You touch the rail, it's very cold. Now you leave them there, and you come back at 1 or 2 in the afternoon. Now you touch the rail, and it's very hot. You can hardly put your hand on it. It's so hot. You put your finger in the water, and it's a bit warmer, but it's not. It's not hot, it's just a bit warmer than it was before. So you'll notice that the temperature differences between them in the metal railing are extreme. They goes from extreme cold to extreme hot, whereas the water goes from kind of cool to kind of warm. We'll talk about that property of water later on, and that property of different substances later on, why metal goes between these extremes of temperature and water does not. Okay, so the unit of measure for energy, heat, and work is a joule. That's the unit of measure for any kind of energy. It could be sound energy, mechanical energy, throwing a ball, a car moving. It could be heat. Electrical energy is measured in joules. Any type of energy is measured in joules. It's the common unit of measure in the metric system. For example, we want a car to do the work of moving us. To do this, the car must have stored energy called gasoline. In chemistry, the calorie is also used to measure energy. So 1 calorie equals 4.184 joules. And note that this calorie is 1/1000th the amount of energy as calories on food packages. So food packages calories are really called kilocalories. They're 1,000 chemistry calories. So when you see 250 calories on a bag of Doritos, that's really 250,000 of these calories, of these types of calories that we use in chemistry. So again, those are called kilocalories, what are on food packages. And you use a capital C to denote food calories as opposed to chemistry calories, which are the lowercase c. So we're interested in chemistry calories. We'll never talk about food calories in this class. So thermodynamic analysis is usually divided into two spaces. The system is what is being analyzed. It could be a single atom or a container of substances. For our purposes, system is where the chemical reaction is taking place. Then outside of the system, or it could be in the same location, you have surroundings. Surroundings is everything outside of the system. It's outside of the place where the chemical reaction that we're studying is taking place. When you take the system and the surroundings together, that's called the universe. The universe is the system and surroundings together. It doesn't mean the literal universe of all the stars and planets and galaxies. It just means the container on in the lab station, in the lab where we're working, in which the chemical reaction is taking place, that contains both the system and the surroundings. That's what we refer to as the universe. Okay, so here's an example. In a chemistry lab, the surroundings can be a sealed container which does not allow heat to enter or leave. So the blue arrows with the red X's means that nothing can enter or exit that container. Neither the material inside the container nor the heat that's generated inside that container cannot go in or out of that solid black line there. So the system can exchange heat energy, the green arrows, with the surroundings. So the system is, you can think of as a smaller container. It doesn't necessarily have to be a container. We're going to talk about that in a while. But for simplicity, just think of it as a small container inside of the surroundings. So heat can go into and come out of the system. That's where the chemical reaction that we're studying is taking place. And it can come out into the surroundings. But it cannot go out of the surroundings through that thick black line into the outside world. The surroundings cannot exchange heat energy, the blue arrows, with the outside world. In a controlled experiment, the universe is the system and surroundings together. The universe does not include space outside of the defined system and surroundings. So anything outside of that thick black line is not part of the universe that we're talking about. We're talking about a very limited universe, which is simply the system and the surroundings inside of the thick dark black line there. Okay? All right, so let's define several types of systems. Closed systems can exchange energy but not matter with the surroundings. These are systems that we will use. So a sealed coffee cup can exchange energy but not matter with the environment. So you can't spill the coffee out of that cup, but heat can come out of that cup. An open system can exchange both energy and matter with the surroundings. So an open coffee cup can be poured out so it can exchange both matter and energy with the surroundings. And then isolated systems, you can think of that like a thermos. Isolated systems cannot exchange either energy or matter with the surroundings, such as a thermos that keeps hot liquids hot. The system and surroundings together are called the universe. So system plus surroundings equals universe. Any energy that leaves the system must enter the surroundings, and any energy going into the system must have come from the surroundings. So this is expressed by the formula delta E, which means change in energy in the system equals negative delta E of the surroundings. So if you add energy to the system, you've subtracted that much energy from the surroundings. And if energy goes out of the system into the surroundings, that would be negative energy for the system. That same amount of positive energy, positive E delta E, would go into the surroundings. So the two have to always be equal and opposite. The first law of thermodynamics states the energy is conserved, which means the energy is not created or destroyed. Energy can be converted from one form to another, such as heat, electricity, or mechanical. And so again, we see the relationship between energy, work, and heat is the following. Delta E equals Q plus W. Delta E is the change in energy. Q is the heat added to the system. W is the work done on the system. That's work added to the system. So positive always means something going into the system. Again, think of it like, think of it like money going into your bank account. If money goes into your bank account, that's positive. If money comes out of your bank account, that's negative to your bank account. Energy going into the system is positive. Energy coming out of the system, or work coming out of the system, both either energy or work, is negative. When work or heat are put into the system, the number is positive. When work or heat are removed, the number is negative. So here's a little illustration to show that. When heat or work goes into the system, it's positive. That's your bank account. When heat or work come out of the system, that's negative. When heat enters a chemical reaction system, the reaction is endothermic. Just think of the word meaning endothermic. It's going in. When heat leaves a chemical reaction, the reaction is exothermic. Just think of an exit sign above a door. It means you're going out. A state function is a function that only cares about the value you added at, the value you ended at, and not how you got there. Internal energy, delta E, is a state function. So here's an example of a state function. If you begin a walk at 0 feet above sea level and end on the top of a hill 1,000 feet above sea level, it doesn't matter what path you took. Your elevation change was 1,000 feet. You could take a path that goes straight up to the top, or you could take one that kind of goes up and down and up and down, and finally you end up at the top. It doesn't matter. In both cases, you'll have an elevation change of 1,000 feet. That's an example of a state function. So a similar example related to chemistry here. In one case, you heat water to 100 degrees and then cool it to 50 degrees. In the second case, you cool the water to 0 degrees and heat it to 50 degrees. The only thing that matters is that the final temperature is 50 degrees. Okay, so that's an example of a state function. In other words, it doesn't matter what path you take to get to the final destination, it's just what the final destination is. So if a system produces 1,000 joules of energy, it could be by putting out 600 joules of work and 400 joules of heat, or 100 joules of work and 900 joules of heat, or any combination of heat and work that add to 1,000 joules. So energy is a state function, but heat and work are not. So state functions are energy, any form of energy, temperature, pressure. It's just what do you end up with. Not state functions would be work and heat. Now let me just say, we're not going to deal much with state functions. You'll probably hardly ever hear the word again. But when you get into, if you were to go to college and take a full-on class in thermodynamics, you would deal with state functions a lot more. We don't deal with it that much here. Alright, so we've talked about solids, liquids, and gases quite a bit. Solids are rigid. They have a fixed shape and a fixed volume amount of space they take up. They can't be compressed. It says squashed down there. They can't be compressed is really the proper word. Liquids are not rigid. They have no fixed shape. So you can pour water from a tall, narrow glass into a short, wide glass, but you have the same amount of water, so that's fixed volume. They also can't be compressed. The molecules are all next to each other. Gases, which we talked about last week, are not rigid. They have no fixed shape and no fixed volume. So you can take a bottle of perfume where all the perfume molecules are inside that little bottle, open it up, 15 minutes later you can smell it throughout the entire room. That means the perfume molecules have expanded in volume and they now take up the shape of the room. So solids, liquids, and gases are called states of matter. States of matter determine how atoms' molecules connect to one another. Solid, atoms' molecules are in fixed positions, for example, ice. Liquid, molecules are attracted to each other but can move, example, water. Gas, molecules are detached from one another and can move freely, example, steam. Solids have the least energy, gases have the most energy. Enthalpy. This is a key word that become familiar with this. Enthalpy is the amount of heat taken in or released by a chemical reaction under constant pressure. Don't worry too much about the constant pressure. We're just going to assume that in almost every example that we give. In chemistry, we are interested in changes in enthalpy that take place during a chemical reaction. Change in enthalpy is represented by delta H. So change in enthalpy, delta H equals heat at constant pressure. So if heat goes into a chemical reaction, that's positive enthalpy, that's positive delta H. If heat comes out of a chemical reaction, and that's usually what happens, but not always, that's negative delta H. So negative delta H is heat coming out, positive delta H is heat going in. Heat going into a chemical reaction is positive endothermic, and heat leaving the reaction is negative exothermic. So keep that relationship in mind. All right, there are several types of enthalpy that we're going to study. The enthalpy of fusion, fusion means to put two things together. The enthalpy is associated with a phase change between a liquid and a solid, such as melting ice. So the amount of heat that it takes to melt a certain amount of ice is called the heat of fusion. The amount of heat that you have to take out of a certain amount of water to make it freeze into ice, in fact, is called also the heat of fusion. It's just one is negative and one is positive. If the heat is going in to make the ice melt, then that would be a positive heat of fusion. If the heat is coming out to make the ice freeze, if you want water to freeze into ice, you have to pull heat out of it, then that would be a negative heat of or enthalpy of fusion. Enthalpy of vaporization is the same thing between liquid water and steam or boiling water. The enthalpy associated with a phase change between a liquid and a gas, such as water to steam. So if you put heat into water to make it boil and evaporate, totally evaporate, that's a positive heat of vaporization. If you take steam and take the energy out of it, pull the heat out of it so it condenses back down into liquid water, that would be a negative heat of vaporization or enthalpy of vaporization. Enthalpy of reaction, the enthalpy produced by a specific chemical reaction. We're going to be dealing with that a lot. How much heat is given off or taken in when a chemical reaction takes place. And enthalpy of formation, that's a unique one. The enthalpy required to produce 1 mole of a particular compound. So if you want to produce 1 mole of carbon dioxide from carbon and from an oxygen molecule, the amount of energy that would go in or come out of that reaction to make that happen is called the enthalpy of formation. And by the way, for all of these, the three enthalpies up above, fusion, vaporization, reaction, if you measure it for 1 mole of the substance, it's called the molar. So molar heat of fusion, molar enthalpy of fusion, molar enthalpy of vaporization, molar enthalpy of reaction. It's the amount of heat that it would take to make 1 mole of the substance do any of those things. All right, the letters after each product and reactant reflect the state of matter. There are 4 possible values that they can display. Solid, which is what you would think it is. Liquid, which is a pure liquid like pure water. We've talked about that. Gas, which is a vapor or unattached molecules of some sort. And aqueous solution. So we've talked about what the difference is between that and a liquid. It's something mixed into water, and that's AQ. So those are the 4 states of matter that you'll see after the reactants or products of a chemical reaction. The state, liquid, gas, or solid of the products and reactants affect the enthalpy values of the reaction. So for example, if you want to turn something into gas vapor, into steam, if you want to produce water that's turned into vapor, water vapor, gas, not as much energy will come out of that reaction because the vapor has higher energy than liquid water. But if you want to produce water that's in liquid form, you have to pull more energy out of it. So that will have a higher enthalpy of reaction to produce liquid water, because you pull more energy out of it to cause it to condense down into water. We'll see plenty of examples of that. Okay, the balanced chemical equation for the combustion of methane out of the chemistry lab, that's the gas that comes out of the valves in the chemistry lab, can be expressed as follows. So it's CH4 plus 2, and it's CH4 gas in gas form plus 2O2 in gas form will give us CO2 in gas form. And then the H2O could either be in liquid or gas form. If it's in liquid form, what delta H negative 890 kilojoules means is that 890 kilojoules of energy will come out of that reaction from the system, which is where the reaction is taking place, into the surroundings. So negative 890 means that much heat is coming out, that much heat energy, 890,000 joules, is coming out of the system and into the surroundings. If that water had been gas, vapor form, then that vapor would have had more energy, so that means it wouldn't have had to give off as much energy. So that figure is not 890, it's about 820 kilojoules. Okay, the equation states that when 1 mole of methane, CH4, is combusted, burned, it releases 890 kilojoules of heat energy. The states of matter are shown in parentheses after each reactant or product. Okay, now extensive property. An extensive property is a property that depends on the amount of matter being used. An example would be mass or volume. An intensive property is a property that is independent of the amount of matter. An example would be density. So for example, water has a density of 1 gram per milliliter. It doesn't matter how many grams of water you have, the density is always going to be 1 gram per milliliter. So the rules of enthalpy. Enthalpy depends on the amounts, masses of reactants and products making it an extensive property. So if you want to produce more water than is shown in that chemical reaction up above, you're going to have more heat coming out. So that would be an extensive property. It depends on how much water, how many moles of water you want to make. The enthalpy of a reaction is the same as the enthalpy of a reverse reaction, but the opposite sign. So in other words, if you wanted to take that reaction up above and take the water and the carbon dioxide and pull it apart and go backwards to make CH4 and O2, then the enthalpy would be the same, except you'd take the negative sign off the 890 and it would be positive 890. So in other words, you can turn a reaction around, and we'll see examples of that in this particular unit. You can turn the reaction around so the CO2 and H2O are on the left and the CH4 and O2 are on the right, and the delta H for that would be positive 890 kilojoules. And third, enthalpy depends on the state, solid, liquid, gas of reactants and products. So that's what I just mentioned. If you want the water to be in liquid form versus water vapor, it's going to be a different enthalpy because you have to take a different amount of energy out of it. Okay, the enthalpy needed to turn liquid water into gas or steam is 88 kilojoules. So in other words, instead of 890, it would be, I said about 820. It's more like about 810 or 812 kilojoules. If you wanted to turn that water up above into steam rather than liquid, not as much energy would come out. Why? Because some of the energy has to stay in the water to keep it as steam, so it won't condense down into liquid. All right, let's deal with some important terms that we're going to be dealing with in this unit. Specific heat capacity and heat capacity. So specific heat capacity is defined as the amount of heat required to raise 1 gram of a substance by 1 degree. The degree could either be in Kelvin or centigrade. It doesn't matter because 1 degree on those scales is the same. It doesn't matter which scale you use. Heat capacity is the specific heat of a substance multiplied by the mass. In other words, heat capacity is an extensive property. It depends on how much matter you use. It takes more heat to heat up a swimming pool than it does to heat up a pan of water. So you would have to take into account how much water you have for heat capacity. Specific heat capacity is how much heat does it take to raise 1 gram, a very specific amount of water, by 1 degree Kelvin. So understand the difference between the two. In other words, and I'll mention this down lower, the heat capacity is equal to specific heat times the mass of the substance. So specific heat capacity applies to 1 gram of substance. Heat capacity applies to the entire mass of the object being measured. Now this formula down here is maybe the most important formula we're going to deal with this week. It relates heat to temperature. Oftentimes people talk about heat and temperature like they're the same thing. Something's high temperature, it's got a lot of heat. But remember the difference. Temperature is internal to the object. It's the internal kinetic energy of the object. And we measure it on something called a thermometer. Heat is a transfer of heat energy, thermal energy, between an object at higher temperature to an object at lower temperature. So if no energy transfers, there's no heat. So the energy, in other words, has to come out of the object and go over to another object. And that other object could be the air. It could just be the atmosphere. So as we see this formula down here, it says the amount of heat is equal to the mass times the specific heat of the substance times the change in temperature. So we look at what that means down here. So Q is heat in joules. Q is heat in joules. M is the mass in grams. And C is the specific heat. And that's a characteristic of a particular substance. So let's go back up and look at this table. So there are some specific heat capacities. This comes from your book. So you see water is 4.18 joules per gram Kelvin. Okay, so that's how much energy heat you're going to get for every gram that you use of water, in the case of water, and every degree Kelvin that you raise it. So for water, it's 4.18. If we look over on the left at some of the metals like aluminum and iron, we notice they have very low specific heat capacities. And we're going to see how that affects their temperature change. We know intuitively, we've experienced how the temperature of a metal changes compared to water, and we're going to see how that's calculated down here below. Okay, so there is a table of those, and if you ever need to work one in a problem, it will be given to you, or you will be given a table to use to look it up. So Q is heat in joules, M is mass in grams, C is the specific heat, and it's measured in joules per gram Kelvin or joules per gram centigrade. Again, 1 degree on either of those scales is the same. The delta T is the change in temperature. So you can rearrange that equation. The equation can also be written in terms of change in temperature. So delta T equals Q over MC. So heat divided by the heat that either goes in or out, divided by the mass of the substance, how much of the substance you have, in other words, and the specific heat, which is a characteristic of a particular substance. Every substance has its own specific heat. Okay, so if delta T, so if delta T is negative, then Q is negative, and the reaction is exothermic. In other words, if the temperature goes down in a substance, that means it must have given off heat. That would be an exothermic reaction, and it means the delta H would be negative. If delta T is positive, then the reaction is endothermic. That means heat had to go into the object to raise its temperature. Example. So here's the example I gave earlier. Think of touching a cup of water sitting next to an iron bar on a normal morning. The cup of water will be cool and the iron bar will be cold. Now it's 2 p.m. and you touch the same cup of water and the iron bar. The water will be warmer, but it's not hot, it's just a little bit warmer. The iron bar, however, will be very hot. So a high specific heat means that the amount of heat, a particular amount of heat, will not change the temperature of an object very much. A small specific heat means that the same amount of heat will cause a greater temperature change. So let's use the formula and we can see an example of this. So, example. We can use the equation to see how the temperature of 1 gram of each substance will change if 10 joules of heat are added. So what we're going to do is add 10 joules of heat from the sun to an iron bar and 10 joules of heat from the sun to a cup of water. So you plug in the numbers, you have delta T equals Q over MC, so it's 10 joules for Q, 1 gram for the mass, and 0.45 joules per gram Kelvin for the iron. That's a number that's specific to iron, that 0.45. When you do the math, that 10 joules will cause the temperature of the iron bar to go up by 22.2 degrees Kelvin. Now what if you do the same thing to water? You put 10 joules into that. You also have 1 gram, but notice that the specific heat of water is 4.18 joules per gram Kelvin, much higher number than for iron. When you do the math on that, you get a temperature increase of only 2.39 Kelvin. So the iron goes up 10 times as much as the water, the temperature of the iron. So the same amount of heat added causes the temperature of the iron to rise almost 10 times as much as water, which explains why the temperature extremes in iron are much greater. Why the iron bar gets really hot on a hot afternoon and really cold on a cold morning. Substances with low specific heat values will experience greater temperature changes when heat is added or removed. Also, small changes in temperature of these substances will take in or release large amounts of heat. Specific heat is an intensive property because it does not depend on mass. So the specific heat of iron is 0.45, whether you just have a little bit of iron or a huge amount of iron. That's called an intensive property. The amount doesn't matter. Its specific heat is always going to be 0.45. And for water, it's always going to be 4.18, whether you have a little cup of water or a big swimming pool of water. The specific heat is going to be the same. Heat capacity is an extensive property because it does depend on the mass of the substance. So in other words, even though water has the specific heat of 4.18, no matter how much you have, it's going to take more heat to raise the temperature of a swimming pool than it will of a small cup of water. So down there is the relationship between the two. Heat capacity equals the specific heat capacity times mass. All right, so this wraps up this first lesson for the thermochemistry unit. We'll move on to some others in the next couple days. I'll have actually the next one up later today. It's Tuesday, October 27th, and I'll have that up later. All right, so use this lesson to answer the first set of questions. Have a good day.